Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 6 on exploring the circle area formula. In today's lesson what we're going to be doing is we're going to be trying to come to grips with why the area of a circle is pi r squared. So let's play around with that a little bit. You're definitely going to want to have your graphing calculator on because we're going to be doing a little bit of trigonometry later, so make sure to have that handy. But let's start by beginning to talk about something that's probably pretty obvious, but is important anyway, the similarity of circles. Now in the last lesson, we reviewed the formula for calculating the area or space that lies within a circle. There are many ways of deriving this formula, but all of them involve calculus. In this lesson, we will explore where this formula comes from more informally. First, we start with a simple idea, the idea that all circles are similar. Now, I just want to point out, that is not true of most shapes. Not all rectangles are similar, not all parallelograms are similar, not all triangles are similar, all squares are similar, all right? But what is certainly true is all circles are similar. Now remember, way back when we talked about similarity, the way that we defined similarity was if there was a similarity transformation, that mapped one figure on top of the other, then they had to be similar to one another. Specifically, what a similarity transformation was a combination of a dilation along with one or more rigid body motions, those rigid motions being translations, reflections, and rotations. All right, so just a little bit of a review of that. Let's take a look at exercise number 1. For each of the diagrams below, give a similarity transformation that would map circle A onto circle B, be as specific as possible. All right, so if I wanted to map this circle onto this circle, what would I do? I want all the points in this pre-image to end up lying all along the points on this image, What would I do? Pause the video now and see if you can think about what the similarity transformation would be. There's going to be 2 steps, let me give you that as a hint, and they should be, I think, fairly obvious. All right, well the first thing I want is I want the center of my image of this to lie on that center. All right, so the first thing I'm going to do, is I'm going to translate circle A so that point A maps to point B. All right, so that's my first thing. Now, I want you to just kind of visualize that, If I did that, if I shifted this entire circle over, every point coming along with it, I would end up having, that looks terrible. This is where it would have been helpful to just have a magic like circle A that I could move over. But I would suddenly have circle A kind of here, but now it would be A prime sitting there. All right, now think about it. Every point on A prime, is 2 units away from point B or point A prime. They're the same point at this point, I want to stretch that out so that every point now lies 6 centimeters away from the center. And that's easy enough to do. All I now have to do is dilate circle A prime using point B as a center and a scale factor equal to 3. That's it, Because if I suddenly stretch this thing out with a center equal to B, remember the center of a dilation doesn't go anywhere, then every point that used to be 2 centimeters away from B now will be 6 centimeters away from B, Because that's the definition of a dilation. We're just moving every point by that scale factor so that it's that many times larger away from the center than it was to begin with. All right, so it's simple, Now, that's a very specific case showing that a circle with a radius of 2 is similar to a circle with a radius of 6. Now let's do it in general when I've got a circle with a radius of r1 and a circle with a radius of r2. See if you can write down a similarity transformation that will map circle A onto circle B. All right, well, step one is the same as above. And I'm going to literally write that down, and I would suggest you do as well. Same as step one above. All right, in other words, right, the first thing that I would do is I would simply translate circle A so that point A maps to point B, right? I just want this thing to line up so that the two circles have the same center. This one now has a radius of R1, that one has a radius of R2. Now, the tricky thing, right, is what always happens when I've got these sort of abstract things, R2 and R1, right? But keep in mind, whenever I did similarity transformations before, I would always take the new image length divided by the old image length. So I'm going to do, in number 2, same as step 2 above, except with a scale factor equal to R2 divided by R1. Right, and it kind of makes sense, because if you think about it, right, if you got this point that's a distance of R1 away from B, right, when we then multiply it by R2 divided by R1, right, those cancel, and now we are a distance of R2 away. And that's exactly what we had before, right? We had 6 divided by 2, which was a scale factor of 3. If I had, R2 was 10 and R1 was 2, I'd have 10 divided by 2, we'd have a scale factor of 5. And it can even go the other way around. R2 could be smaller than R1. So if R2 was equal to 2 and R1 was equal to 6, then I'd have 2/6, or a scale factor of 1/3, right? And this basically gets the job done. It means that using a translation and a dilation with a scale constant at the center of the circles, right, with a ratio of R2 divided by R1, will always map one circle on top of the other, which means the circles are similar to each other. And that is very critical. All circles are similar to each other. And now let's see how we can use that fact to help us understand why the area formula of a circle must be pi times the radius squared. Here we go. First observation about circle area. The fact that all circles are similar leads us to our first fact about the area of a circle. Let's take a look at exercise number 2. Consider circle A whose radius is equal to 1 and circle B whose radius is equal to R. All right. This is really critical, so let's talk about this. I've now got, right, similar scenario to the last problem. I've got a circle whose radius is equal to 1. That could be 1 centimeter, 1 inch, 1 mile, 1 foot, I don't care. And then I've got circle B that has a radius that's equal to R, and keep in mind that circle B, R could be smaller than 1, it could be larger than 1, it doesn't matter. Let's take a look at letter B. Or sorry, letter A. What scaling factor K would be needed to map circle A so that it was congruent to circle B? In other words, if you were going to do exactly what we just did in the last problem, proving that these two circles were similar, what would your scaling constant have to be? Pause the video now and go ahead and tell me. Well, it'd have to be R. Right? That's what it'd have to be. And the reason why is that, right, remember our scaling constant is R2 divided by R1, right? K would be R2 divided by R1, which is just that generic R divided by 1, and that's just R. So in other words, if R is greater than 1, right, and then we stretch this thing out by a factor of R, then it's going to have a radius of R. And if R is less than 1 and we shrink it, so we multiply this radius by R, it's going to now have a radius of R. So our scaling constant to go from a circle with a radius of 1 to a circle with a radius of R, whether that's bigger or smaller, that scaling constant just is R. Okay, letter B. What does this tell you about the area of circle B compared to the area of circle A? Write it as an equation. All right, so now we just had a lesson, a couple lessons ago, on the areas of similar figures, right? And we said there's a relationship between the area of an image versus the area of the pre-image, and we want to think about this one as the pre-image and this one as being the image, right? If we know what the scale constant is, all right? And remember what that was, forget about this in general, right? right, we learned that the area of the image was always going to be k squared times the area of the pre-image. All right, so given that you know this and you know this, what can you say about the areas of these two circles? How will they relate to each other? Pause the video now and see if you can write something down. Well, what it tells us, right, is that the area of circle B, which is kind of a generic area, is going to be k squared times the area of circle A, which is not generic. It's got a radius of 1. So the area of circle B, now remember k is equal to r, right? So the area of circle B is going to be r squared times the area of circle A, right? Which tells us, right, that the area of any circle is going to be the area of a circle with a radius equal to 1 times r squared. Right? So the area of any circle whatsoever, is going to be the area of a circle whose radius is equal to 1. All right, I don't know what that is, but whatever it is, right, it's going to go in here. Whatever the area of that circle is, it's going to go in here times the radius squared of our new circle. Because all this circle is a dilation of this circle by a scale factor of k, or scale factor of r, sorry. So its area will be scaled by r squared. So now we just have to figure out what the area of a circle is with a radius of 1, and then that's going to be the number that goes in here. And then the area of any circle, right, will be the area of the circle with radius of 1 times r squared. And that just comes directly from our work with both similar figures and with how the ratio or how areas get scaled according to scale constants. All right, so now let's try to figure out what the area of a circle is whose radius is equal to 1. Now to do that, right, so here we go. So now, we now know that the area of any circle is equal to the area of a circle whose radius is 1 multiplied by the square of the radius. But what is the area of a circle whose radius is equal to 1? First, let's do a little bit of trigonometry. Exercise number 3. Determine the area of a regular decagon whose distance from its center to any vertex is equal to 1 unit. Show how you found your answer and round to the nearest thousandth. All right, so this is very similar to when we were looking at perimeters of regular figures. Now we're going to look at areas, and believe it or not, that's actually going to be easier, right? And the reason it's going to be easier, right, is if this length is 1, and you can kind of almost think of that as a radius, right? If that length is 1, this length is 1, okay? And surely I can figure out what the angle is between those two sides, right? And once I know what this angle is, and I'm going to have you think about that in a moment, then I can figure out the area of that one isosceles triangle by just saying, hey, it's 1/2 of 1 times the sine of that angle. And then, of course, I can multiply it by 10 because there's 10 of them. So pause the video now and see if you can use that trigonometry with the area formula of a triangle based on trig to come up with the total area of this decagon to the nearest thousandth. So try not to round until the very end. Pause the video now and play around with this a little bit. All right, well, let's take a look. So obviously we've got 10 of these things all the way around, right? So that angle is going to be 360 degrees divided by 10, which is 36 degrees. So in other words, we've got this isosceles triangle, 1, 1, and 36 degrees. All right? So that particular isosceles triangle, right, the area of just that triangle is going to be 1/2 times 1 times 1 times the sine of 36 degrees. Now, I could figure out what that area is, and that would be lovely, but it would be ugly, long decimal, things like that. Might as well go for all of it, right? So now what I'm going to do is I'm going to multiply by 10 because there are 10 of them. So now my area of my decagon is going to be 10 times 1/2 times 1 times 1 times the sine of 36 degrees. And if I really wanted to, I could do the 10 times the 1/2 times the 1 times the 1 and figure that out. I'm just going to slap this all into my calculator. That's all I'm going to do, right? So I'm going to take this thing out. I'm going to have 10 times 1/2 times 1 times 1 times the sine of 36 degrees, and the area of that decagon is equal to 2.939, accurate to the nearest thousandth, 2.939. Now you probably can already see where we're going to go with this, right? This decagon is not quite a circle, right, whose radius is 1, but it's getting there, right? In fact, what we want to do is we want to take it up a notch. Let's go with like 15 sides, 20 sides, 30 sides. Let's see if we can develop a pattern, because all we need to do is figure out what the area is of a circle whose radius is equal to 1, right? And then we know that the area of any circle is that number times r squared. Let's take a look at exercise number 4. Below are images of regular polygons, each of which has a distance from its center to any vertex of 1 unit. Determine the area of each to the nearest hundredth. Now, as you saw, right, the real key is, in every case, we're going to slice up these regular polygons into a bunch of isosceles triangles, right? And we're going to have as many isosceles triangles as we do side lengths. This one's going to have 15, pi pieces, this one's going to have 20, this one's going to have 30, right? We just have to be able to figure out what that angle is. That's the only hard part, right? Now with 15 sides, right, my angle is going to be 360 divided by 15. So let's figure that out, right? My angle, 360 divided by 15, 24 degrees, nice angle. Right? So now any individual one of the things is going to have 1/2 times 1 times 1 times the sine of 24. So my total area is going to be 15 times 1/2 times 1 times 1 times the sine of 24 degrees. Right? That's so simple. It's much easier than what we did when we had perimeter, because with perimeter we actually had to have a right triangle, which meant we had to divide each of the sides by 2. The angle got divided by twice the number of sides. It was just messy, right? Here it's easy. 15 triangles. The angle comes from taking 360 and divided by 15, right? That gets into that whole rotational symmetry thing. Anyway, let's figure out what this thing's equal to. So the area of that 15agon, I'm sure that's not what it's actually called, is 15 times 1, whoops, I messed that one up. 15 times, I'm going to use 0.5 as 1/2 times 1 times 1 times the sine of 24. And that's now going to be the area total is equal to 3.050 to the nearest thousandth. Okay. Great, awesome, right? So we're getting closer, right? And the more sides we have, the more the figure is going to look like a circle. In fact, again, depending on how small of a screen you're looking at, this might already look like a circle to you. It pretty much looks like a circle to me, but I have bad eyes. So what I'd like you to do now is take a moment and try to figure out what the areas of each of those particular circles are. And they're going to be close to this. They're going to be not that much different than 3.050. Pause the video now and play around with it. All right, so let's do our thing. Let's get our angle. And our angle is going to be now 360 divided by 20, which is going to be 18 degrees. All right, so our total area is going to be 20 times 1/2 times 1 times 1 times the sine of 18 degrees. And actually, maybe I can just go up and grab this, hit enter. Always debatable whether this is faster, but let's try it. All right, we just have to change the number of sides and the angle. And that should do it. And we get the total area, in this case, pretty close to being the same as before, 3.090. All right. And I can even take it a little bit further, right? I don't really even need to know the angle, right? The angle is simply going to be 360 divided by how many sides there are. So I'm going to go right for it right here. The total area here is going to be 30 times 1/2 times 1 times 1 times the sine of 360 divided by 30. Now, if you went ahead and figured out that that was 12 degrees, more power to you, nothing wrong with that. But I really don't need to particularly know what the angle is because my calculator can figure out 360 divided by 30 for me. So actually, let me erase this and just do it that way. I'm going to do 30 times 1/2 times 1 times 1 times the sine. And now let me put that fraction in of 360 divided by 30. All right, let me get out of there. And that, with 30 sides, is going to be 3.119. By the way, if you were waiting for that number to turn out to be something nice, you're probably going to be a little bit disappointed, okay? Now, we're getting very close to getting a firm grip on what the area of a circle is with a radius of 1. And again, keep in mind, the area of a more generic circle with a radius of r is going to be whatever the area of the circle is with a radius of 1 times r squared due to just similarity and scaling. So, let's take a look at letter D. Without a diagram, determine the area of a regular polygon with 1,000 sides. Write out all digits your calculator gives you. Compare it to the value of pi. All right, now you can imagine, given how close this looks to a circle with 30 sides, a circle with 1,000 sides, that's going to definitely, sorry, not a circle, circle has one side. A polygon with 1,000 sides is definitely going to look circular. And what you want to do to figure this out is take this approach. Don't figure out what the angle is. You're going to have 1,000 there, and you're going to have 360 divided by 1,000 there, all right, which is 0.360. So I guess you could do it that way. But why don't you go ahead and figure out that value? All right, let's do it. So this is kind of cool because you could take this as high up as you want, right? This area total is going to be 1,000 times 1/2 times 1 times 1 times the sine of 360 degrees divided by 1,000. All right, those are very small angles at that point, which makes sense. And now that is going to be 1,000. Oh, 1,000 times 1/2 times 1 times 1 times the sine of 360 divided by 1,000, that's 100, times 1,000, and a circle, and it says write out every digit your calculator gives you. And of course, that's going to depend on how many digits your calculator is currently set to give you, right? So you might not get as many digits as mine. If your calculator is set to like a 3-digit rounding or a 5, mine is set to like, I don't know, 14-digit rounding or something like that. Now, you've probably been around the block long enough to recognize that this is getting very close to the value of pi. Okay, very close. And in fact, the value of pi, okay, accurate to however many decimals my calculator is showing me, is 3.14159265359, and these two are the same all the way out to there. All right, which is exceptionally accurate, right? If you're talking about out to 4 decimal places, and that's only 1,000 sides, right? We can think about a circle, as we mentioned back in our circumference work, we can think about a circle as being a regular polygon that has an infinite number of infinitesimally small sides. So 1,000, although it's large, is nowhere close to an infinite number. But if you want to keep playing around with this, which is cool, you could put 10,000 here and 10,000 there. You could put 1,000,000 here and 1,000,000 here. Eventually your calculator will bail on you and give you probably some kind of an error just because it can't handle that many decimals, so to speak. but we've got it, right? The area of a circle whose radius is equal to 1 is equal to the number pi, right? Whatever the value of pi is, right? It's equal to pi. And that's letter E, right? Since it now appears that the area of a circle with a radius of 1 is equal to pi, what can we now say the area of a circle with a radius of r is? Well, remember that whole point was that the area of a circle with a radius of r was going to be area of a circle with a radius of 1 times r squared. So therefore, that's pi times r squared. All right. There was never any doubt that the area was going to be some number times r squared. The question was, what's that number going to be? Now, this is an approach, right, to understanding the area formula that uses the similarity of all circles, along with the area formula for a triangle that's dependent upon trig to sort of, if you will, get an approximation for the number pi. We're going to look at one more way to think about the area formula of a circle that actually then depends on the circumference of a circle. Let's take a look at that. And it's kind of a neat way of looking at it. Rearranging a circle. There's another way of looking at the area formula for a circle that involves slicing it up and rearranging it. Let's take a look at that. Exercise number 5. Examine the additional handout on circle dissection diagrams. On the sheet, the same circle has been sliced repeatedly and rearranged. The first such rearrangement is shown below. All right, now I don't have that like worksheet up and handy, but of course these are the pictures that you see on it, so hopefully you're taking a look at those right now. And again, I just want to point out that all I've kind of done in this situation is I've taken a circle, not with a radius of 1, with a radius of r, and I've kind of cut it up into equal-sized pi pieces, and then I've sort of alternatingly put them like that. Then I've cut it into 8 pi piece slices and done that, 10 and done that, 16 and done that, etc., right? So just to understand what's going on. Now, let's take a look at letter A. What must be true about the area of the rearranged circle portions, which are called sectors, compared to the original area of the circle? What must be true about the area of that versus the area of that? Pause the video right now and hopefully state the obvious. Well, the two areas will be the same, because we haven't thrown anything away, right? We've just rearranged it. They will have equal areas because no area is lost when rearranging. I should probably say no area is lost or gained when rearranging, but we'll just kind of leave it at that, right? All I'm doing, I'm taking a pizza, I'm slicing it into slices, and I'm rearranging those slices so that they kind of alternate, one up, one down, one up, one down. Okay. Now, let's take a look at letter B. What must be the combined length of the outer curved portions of the rearranged shape? Express your answer in terms of the circle's radius, r. In other words, I'm asking you, if I added up this length to this length to this length to this length, all right, so I'm going to ignore those two straight lengths there and there, what would that length be equal to in terms of the circle's radius, r? Pause the video right now and think about this for a moment. It should also be pretty obvious. Well, that's just the circumference. That's all it is, right? So it's just the circumference. And I know that we're used to thinking about the circumference as pi times the diameter, but here we need it in terms of the radius. So it's 2 pi times the radius, right? So if I add this to this, to this to this, I get the circumference of the circle. It's 2 pi times the radius. Now, let's take a look at letter C. Looking at the circle dissection diagrams, what does the rearranged shape start to look like as the number of slices, parentheses, sectors, increases? So if I look at this, right, at first it looks like this kind of bumpy sort of thing like that, right? And then, as it goes on and on and on, what is it looking more and more like? Go ahead and pause the video and write something down. Well, again, if I squinted and I removed sort of all of these kind of lines that are in between, especially if I look at this one, this is looking more and more like a parallelogram or possibly even like a rectangle, right? Because it's getting more slanted to less slanted, right? This is starting to get more and more vertical, so it's really starting to look like a parallelogram slash rectangle, right? And the cool thing is, we know how to calculate the area of parallelograms and rectangles. It's base times height, right? That's all it is. So now let's get to the coup de grace, letter D. If the number of slices goes to infinity, the rearranged shape is shown below. Fill in the height and the width of the shape in terms of the radius r, and then give its area, right? So again, think about this, right? This is a pretty good approximation of this, and that's only with 30 of them, right? That's just with 30 of them. Now, right, when that's happening, keep in mind that all of these slanted sides on the end are the radii. So what's going to happen, right, is that as this thing kind of keeps getting more and more and more and more like this, right, that height simply becomes the radius of the circle. The width is what's tougher. But keep in mind that all of this and all of this were those curved portions, right, that became kind of flatter and flatter as we started to chop this thing up more and more. Now we knew that in total, right, we had 2 pi r, right? So both the top and the bottom were 2 pi r, which means that that has to just be pi r. In fact, we have a rectangle that kind of looks like this, right? R here, pi r there, and pi r there, because again, the curved portions in total are 2 pi r. That's, you know, the top and the bottom combined. So I have pi r and pi r, but that means the area, remember, is the base times the height, pi r times r, and that's pi r squared. Done. Right? Now, you might say, well, boy, that was a lot easier than the one that we did up to that point with the trig and all of that. The reason that I like doing the other one, right, is that it brings in a lot of good stuff that we've seen before, scaling constants, similarity, right, similarity transformations, the idea that the area of a scaled figure is k squared times the area of the pre-image. All of that is great, and it doesn't already depend on knowing the value of pi. Right? So here we derive the area formula, or we come up with the area formula of a circle based partly on the fact that we know the circumference formula for a circle. We already know the value of pi to come up with this one, right? Whereas in the other one, we didn't have to know it at all. We just discovered it through the use of technology and trigonometry. All right, let's wrap this up. Now, to be clear, in all likelihood, you don't really need to know where either one of these approaches to come up with the area formula of a circle. Although, also to be clear, the standards, the Common Core standards, do state that students will see an informal proof for the area formula for a circle. And we just saw 2 of them. All right, 2 different rationales. So, you know, play around on the homework, you know, see what you can do in terms of like understanding the formula and the approaches that we had. All right, we're certainly going to be using the area formula of a circle in our work going forwards, so it's important to kind of understand where it came from. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.